Hi, I'm Professor Annie Gorden from Auburn University, and we're here to talk about organic chemistry. So we have put together some segments of little things to make them more easily digestible, some things that sometimes we don't always get to spend as much time on in class as we really should, and some things that will help you practice to put these little tidbits together. So up to this point, we've been talking about linear alkanes. So if I have 3 carbons, that's propane. If I have 4 carbons, that's butane. 5 carbons is going to be pentane. And then finally, 6 carbons is going to be hexane. And that's great if we were all in flat world. But we know that we're in a 3-dimensional space. So we need to start thinking about how are we going to put these bigger and bigger molecules together? How are we going to get from a flat N-linear alkane to a larger 3-dimensional structure like cellulose or like a protein? So in order to do that, our first step, our first jump into the 3-dimensional world is to start thinking about ring structures. So if I have a ring of propane with 3 carbons in it, I call that cyclopropane. Okay? 4 carbons would be cyclobutane. 5 carbons would be cyclopentane. And 6 carbons would be cyclohexane. So altogether, these are my cycloalkane structures, where for every carbon that I have, so for N carbons, I'm going to have 2 N hydrogens. So, why is this important? Well, let's look at this now in our thinking about taking it into our 3 dimensions. So, back when we were talking about ring structures, we looked at butane. Remember, butane has torsional strain. That is, we've got free rotation about these bonds, and these bonds are constantly turning because we have electron repulsion from the hydrogens that are repelling each other, causing this to twist. And so these are constantly twisting where the hydrogens get close to each other and they repel each other away. That's torsional strain. Then I have steric strain, where when I have rotation about this bond where the 2 methyl groups, when they come close to each other, they're going to repel each other as well. So that's my steric strain. Right? Now we're going to go from butane to my cyclobutane. Okay? So you can see when I compare these two, in butane I had free rotation about those bonds. In cyclobutane and in cyclopropane, now these bonds are fixed. I can't really turn these bonds. These are in a fixed configuration, a fixed geometry. So there's not really any turn here, and all these hydrogens are going to be very strained because they're going to be eclipsed. They're all going to be on top of each other. Same thing for the cyclopropane. So these are very strained structures. So if you look at our cyclopropane, this bond angle is 60 degrees. And our cyclobutane, this is 90 degrees. Remember, when we had our carbon with 4 hydrogens bonded to it, these hydrogens want to be as far apart as possible from each other. So this bond angle is 109.5 degrees. That's going to give us the least strain. So we're in cyclopropane and cyclobutane. We're in a very strained system. This is ring strain. So when we go to cyclopentane, this bond angle is larger. It's close to 120 degrees. This is going to relieve some of our ring strain, but not all of it. In cyclopentane, right, if this was just flat, you'd see this bond angle would be 120 degrees, and we would still have ring strain. All of my hydrogens would be eclipsed. But now I can twist about these bonds a little bit better. If I take and I twist 1 carbon up and out of the plane, now I can relieve some of that ring strain, and also I can relieve steric strain and torsional strain. If you look at that carbon that's bent up and out of the plane, now the carbons that are on, its hydrogens are staggered, right? So we've relieved some strain that way. And each of those carbons can take a turn bending up and out of the plane to relieve some of the ring strain. When we're drawing our cyclopentane, it can be very tempting to want to draw it like a diamond pointing down. It's actually much easier if you're practicing or if you're in a hurry to draw your cyclopentanes point up. Think about this one like trying to draw a home plate, and think about this one like trying to draw a little house. You've been drawing houses since you were in preschool, so this way is much easier and you're much more used to seeing the structure and looking at it. So let's look at cyclohexane. If cyclohexane was just flat, if I squished it flat, these bond angles would be much too large again, and again, I'd have quite a bit of steric strain from the hydrogens being eclipsed and ring strain from those carbons being bent away from the 109.5 degree angle. But again, I'm more easily able to rotate. Now, if I rotate 2 of the carbons out of the plane, let's rotate 1 carbon up and out of the plane and 1 carbon down and out of the plane. Now, if you look on the edge of these, if you look at each carbon as I turn the cyclohexane around, you can see all of the hydrogens are able to be eclipsed. So we've reduced our steric strain. We've also reduced our ring strain. These carbons are now each closer to that 109.5 degree angle. So by having 1 carbon up and 1 carbon down, right, now all the carbons can be closer to 109.5 degrees. We've relieved ring strain, we've relieved torsional strain, and we've relieved steric strain. So this is great. When we have 1 carbon like this bent up and 1 carbon like this bent down, this is called a chair conformation, and we see these a lot. If you think about our cyclohexane, right, like this, that's flat. When we're drawing a chair conformation, we're thinking about looking at it edge on. And having some practice drawing a chair conformation can be really helpful. You can sometimes find these at the art store. This is just a little stencil. Just the practice of drawing little hexane, just that muscle memory practice will help, but it's also good to have a chance to sit and practice thinking about these in 3 dimensions. So if we're trying to represent this in 3 dimensions, we're going to look at the cyclohexane on the side. When you draw your cyclohexane, think about making it spaced out such that you have 2 parallel lines that are about the 2/3 of the length that they are apart. I'll show you what I'm talking about. Let's have 1 bond like this and 1 bond like that. All right, so they're about 2/3 of the distance that they are apart from each other. Okay, that's 4 of our carbons. Now we have to put the other 2 carbons on. Remember, we want to have 1 carbon going up and 1 carbon going down. So in order to get this and to get it to look right, think about drawing it like an equilateral triangle, okay, where this is the 3rd side of the triangle, right? Okay. If you have to leave those little dash bonds in there to help you remember, that's okay. All right, so great. Now we have our chair conformation. So now we need to put the hydrogens onto our cyclohexane. So think about this. We have 6 carbons, so we need to place 12 hydrogens. All right, each of those carbons is going to want to be as close to the tetrahedral geometry as possible. So 3 of them are all going to have 1 hydrogen that's pointing straight up, perpendicular to the plane of the carbon. So we have 1 here, we're going to have 1 here, and 1 here. These 3 guys are called axial because they are perpendicular to the plane of my cyclohexane, and in this case, these guys are axial up. They're all pointing up and away from the plane. So I had 3 that were axial up, and now I'm going to have 3 that are axial down. 1 here, 1 at the point of my chair, and 1 back here. So those are going to be axial down hydrogens. Now, here comes the hard part. I have another group of hydrogens that are going to be in the same plane. So getting the angle on these can sometimes be a little tricky. These are going to be the equatorial hydrogens. So I've got to have equatorial up first, right? So each carbon that had a down axial hydrogen is now going to have equatorial up hydrogen. So when you're drawing your equatorial up, think about that this carbon wants to be as close to tetrahedral as possible. So think about making a 120 degree angle with this bond here. Up like that. So it's 120 degrees here or 120 degrees here. Okay? It would make an equatorial triangle, right, with that bond right there. Okay? So that's our first equatorial hydrogen, right? So there's 1 here. There's 1 here on the other side. Now this one back here is a little tricky. He's going to need to be parallel to this bond here and about the same bond distance. This bond is going to be 90 degrees here, it's going to be about 120 degrees to the new hydrogen that we're putting in. Great. So those are my 3 equatorial up hydrogens. Now, all of my pink hydrogens, they're all on the top side of the cyclohexane, and there are 6 of them. These guys are all cis to each other. Right? All of the yellow hydrogens, pointing in the other direction, these are all on the other side. They're all cis to each other, and I've done them in different colors. The pink ones, then, their relationship to the other ones, they're going to be trans. Okay? So let's put in the rest of those hydrogens. We had equatorial up. We need to have equatorial down. Great. So we've got our first one here. Think about this one. If I carried this bond all the way out to here, I'd be making an equatorial triangle here. So that's my first one. That's the easiest one to make. Okay. This one over here, same thing. Right? The 2 of these should point towards each other. Okay. And then the last one, this one is a little tricky because this carbon is in the bond. Remember, think about this bond is coming forward towards you. Okay? So this bond here needs to be parallel with this one there. Okay? It's also parallel with this one here. Okay? Right. So now I have 6 equatorial hydrogens and my 6 axial hydrogens. And so this will be very important again later when we get to drawing sugars, and we'll have some of these carbons replaced with oxygens. And when we